Your next unit for rates of change, this is the big one, the difference quotient. This is what's really going to lead you into first principles of calculus. So we're still going to calculate the IROC, but instead of doing a bunch of tedious AROC calculations, we're going to use something called the difference quotient, which you might find tedious as well, or a bunch of tedious steps, but we don't have to worry about doing as much calculator work. And this is actually going to give us a more exact answer. So the different quotient formula. Now I'm actually going to write something here. I don't actually want it to say formula. So I'm going to scratch that out. I'm going to write this. The IROC, instantaneous rate of change, equals the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Now that's a lot, so you might want to copy that down, then pause it, then come back. Again, how you read that. The limit as h goes to 0. Now, if you recall from the last lesson, calculating IROCs using intervals, basically we want to know what the instantaneous rate of change is at a specific value of x. X equals a, let's say. And what we did is we took intervals and we got closer and closer and closer to it. We added or subtracted some value h. We subtracted or added 1. We subtracted or added 0.5, 0.1, 0.01, and you could keep going, 0.001. And we came up with an approximation, and it was a good approximation. Like as soon as we start seeing a trend, we can kind of approximate, but we don't know for certain doing it that way. So what the difference quotient does, it does the same thing almost. Well, basically the same thing. It computes the slope of the secant line through 2 points. So here's our value. I'll change my color here in my graph. So here's our value x and f of x and y. And what's going to happen is we're going to do x plus h. So we're going to add a little bit to x. So let's say that's at 2. We're going to add a little bit, just like we did in the last lesson. So let's say add a 10th. And then what is that value when you sub it into your function, f of x plus h? But what we're going to do is we're going to do the limit as h goes to 0. And what the limit means is, it means you don't quite get there, but you almost basically do. It's kind of like asking you a question like this. If you were to stand on, let's say, the opposite side of your room and face the opposite wall, doesn't matter, just you're facing an opposite wall. If you were to walk half of the distance remaining between you and the wall every time, would you ever get to the other wall? If you think about it, there's a theoretical answer, and then there's a realistic answer. Theoretically, if you only walked half the distance remaining each time, theoretically you would never get to the wall. It'd be impossible. You'd be very, very close, but you still wouldn't be there. Realistically, the answer is yes, you'd get to the other wall because at some point, your feet just can't walk that small of a distance anymore, right? You'd have to shrink yourself down, and we're talking be nanometers of distance and micrometers, and keeps going on down and down from there. So realistically, yes, you would get to the wall. So that's kind of like the idea behind, it's not a perfect analogy, but it's kind of the idea behind what a limit is. So we're going to move this point right here so close to it that essentially it's going to look like it's right on top of it. There is zero distance between it. Okay? Now the problem becomes that when you're trying to calculate the distance between those 2 points, write the change in x. But the problem becomes that on the bottom of that fraction here with h, remember that's just like your f of b minus f of a all over b minus a. But that distance h gets so small. Again, those 2 points basically, for all intents and purposes, are right on top of each other. Well, that means that your difference in h is 0, and we can never divide by 0. So we have a problem that we're going to learn how to overcome. So again, when you're doing this, these limits, basically your goal is to limit. So basically it means h is going to approach 0. Very, very close to 0. So close, in fact, that you might as well say 0. Technically, it's not 0. You could zoom in with an electron microscope and there would be a fraction of a unit between them. But essentially, it's going to be 0. And that's the key behind what we're doing. Our first example, we are going to estimate the IROC for f of x equals x squared when x equals 3 using the difference quotient. Just so you are aware, on your test, basically the rest of the lessons are only doing difference quotient. On your test, I'm going to force you maybe a couple times to pick one of the interval methods and force you to do difference quotient at least, I don't know, three to four times, let's say. And then the rest of the questions, I'll leave it up to you to pick your choice. You could do an interval method or you could do the difference quotient. But you have to know how to do both. And you will be forced to do them both at least a couple times each on your test. Anyways, the difference quotient. So let's start off with our notation. So our IROC equals the limit as h goes to 0 of f of x plus h minus f of x all over h. Do you have to write that out every time? No, but you should until you got it down pat. So now, technically speaking, the limit as h goes to 0 should be there at every single line of your step. So equals limit as h goes to 0. Next line, equals limit as h goes to 0. As long as you have it in at the beginning and at the end, I'm fine with that. I'm not going to take marks off. I'm not going to be a stickler for that. So again, you need to have it once at the beginning, whether it's you writing out the formula that I just wrote out or your first step of your solution, and then you'll throw it back at the end. I mean, if you want to, you could write it every single time if you really want to, so you don't forget. That's your call. So again, technically limit as h goes to 0 is still there. I'm just not going to write it. X plus h, that's 3 plus h minus f of 3 all over h. Again, our work would be done if we could just put 0 in for h, but we can't divide by 0. So we're going to put f of 3 plus h into my formula, into my function, x squared. So 3 plus h squared minus f of 3. What is f of 3? 3 squared is 9, so minus 9 over h. When you are squaring something, please don't just write 9 plus h squared. That's not actually what it is. You can remember the shortcut to a perfect square binomial, or you can just write two of them in FOIL and collect like terms. Regardless, you'll end up with 9 plus 6h plus h squared minus 9 over h. Now that's convenient for us, because when I go to collect like terms, look what happens. 9 minus 9, 0, they're gone. All I'm left with is h squared plus 6h all over h. That is very, very good news for us, and you're going to see why in a second. Again, our problem is that we can't divide by 0. So eventually, see, our end game is to get rid of that h on the bottom, if we can. At this point, what could you common factor out of the numerator? Well, you could common factor out an h, which would leave you with h plus 6 over h. That is good, because look at this. Those two h's cancel, and all you're left with is h plus 6. And at this point is when you can throw your limit back in, which technically has been there all along. I was just lazy and didn't want to write it. Now it's okay to put 0 in. If I do that, 0 plus 6 equals 6. Therefore, the IROC at x equals 3 is 6. You're calculating the rate of change. If you had to make a sketch, x squared, right? Looks like that. 1, 2, 3, it says right there. We just calculated that to be 6. I don't know how you feel about that. It's the first time you've done it, most of you. Maybe it looks a little intimidating. Maybe we have to review it. We're going to do a bunch of examples. I like this a lot better than the interval method, personally. But I'll leave that up to you. Estimate, and these technically shouldn't really even say estimate anymore. I forgot to take it out of the examples from previously. So we want to know what the IROC is for f of x. And our function is x squared plus 7x minus 2. And again, we'll do it when x equals 3. And we're going to use the difference quotient. IROC equals, I'm not going to bother writing the full solution. I'm just going to go right to f of 3 plus h minus f of 3 all over h. I'm lazy. I'm going to stop writing the limit. You're more than welcome to keep writing it if you would like to. All right, so we got a lot of algebra to do. So I'm going to put 3 plus h in to my function. So 3 plus h squared plus 7 times 3 plus h minus 2. Then minus, right? Minus f of 3. Put 3 in. So 3 squared is 9, 7 times 3 is 21, 21 plus 9 is 30, minus 2 is 28. So minus 28 all over h. Binomial expansion, 9 plus 6h plus h squared, distribute 21 plus 7h minus 30 all over h, and collect like terms. Again, this is good. We have h squared, and then 6h plus 7h is 13h. And then look what we have. 9 plus 21 is 30. Minus 30 is 0. Now we've only done it twice, so doing it twice doesn't make it necessarily a pattern, but that is what you are looking for to determine if you have done things correctly, is get those numbers to cancel so you can factor to get rid of that h. I can common factor an h on top. That leaves me with h plus 13 all over h. Nice, those cancel. I'm ready to pop my limit back in. H plus 13, 0 plus 13, 13. Pretty fancy, eh? Example 2. So we're going to get a little bit more tricky now. So we want to estimate the slope of f of x equals sine x when x equals pi over 2. This is going to be a weird one. Well, let's start where we normally start. IROC equals the limit as h goes to 0, and then f of pi over 2 plus h minus f of pi over 2 all over h. I'm going to stop writing the limit. Sine pi over 2 plus h minus sine pi over 2 all over h. Now there are a couple different ways that you can get to your final answer here, or at least part of the way. You can use a compound angle formula or a cofunction identity if you want. So to get from here to here, I'm just going to make a note. You can use a compound angle formula, so you have that on your formula sheet. That would be the compound angle formula for sine for addition. So like sine pi over 2 cos h plus cos pi over 2 sine h. Or you can use another cofunction identity. It doesn't matter which one you use. I'm going to use the cofunction identity, which sine pi over 2 plus h is just cos h minus, and then sine pi over 2 is 1. So this is minus 1 all over h. If you use the compound angle formula, you would just have 2 extra steps of reducing to get to cos h. If you use the cofunction identity, you can get right there. Make sure if that's the case, that you can use a cofunction identity, that you actually write to me in your solutions that that's what you used, so I know. Otherwise, you have to use the compound angle formulas. So this is going to be somewhat problematic for us. Now you learn how to deal with this in calculus, so I'm not going to go into this too much more for simplifying this. So what I'm going to do when we get as far as we can in the simplification, and this isn't going to happen with linear, polynomial, or rational equations. It's only going to happen with weird ones like trig functions, sine, cos, and tan, and with exponential functions, which we're about to do. Everything else is going to work out neat and tidy like the last 2 examples. We can still handle this though, in a roundabout way. So what I'm going to do, I can't divide by 0, but we do know that basically the idea here is getting very, very close to 0. So what I'm going to do is I'm going to slightly change my limit. So instead of it going to 0, I'm going to say it goes to 0.0001. 3 zeros and a 1. That's pretty close. Of cos h minus 1 over h. This is very, very, very important. When you do this calculation, your calculator has to be in radian mode. In fact, whenever you do these, even if the textbook question gives you degrees, you have to convert them back to pi's. It has to be radians. The difference quotient, which, spoiler alert for calculus, is basically first principles calculating derivatives, is only possible in radian mode, using radians. So you have to make sure your calculator is in radian mode, not in degree mode. You will get a different answer. So we're just going to straight up sub that in. So this equals cos of 0.001 minus 1 all over 0.0001. Type that in, you should get negative 0.00005. That is really close to what? Really close to 0. So therefore, the IROC of f of pi over 2 equals 0. Let's think of the graph to back that claim up. Sine x does that. Pi over 2, pi, 3 pi over 2, 2 pi. Pi over 2, it's right there. That is one of your relative maximums. Comes to a peak. The secant line that goes through two very, very close points at that peak, i.e. a tangent line, is 0. That's a flat line, right? That has 0 slope. And remember, any point that is a relative maxima or minima is always going to have an IROC of 0. If you throw a ball or any object into the air, this is kind of going into physics. If you had the ability to have a stopwatch that could like stop time, so you throw a ball into the air, start the stopwatch. If you had the ability to stop it right at its peak, it's technically not moving for like the smallest little fraction of time. So you throw the ball up, it reaches a maximum, it falls back down into your hand. It changes direction. The rate of change changes. It goes from increasing to decreasing. But at the very peak, it's technically motionless for just the tiniest little bit. It's not increasing or decreasing, it's static in the air at its peak. Everywhere you have a maximum or minimum, you have an IROC of 0. And we're going to use that in the future. Number 3, another weird one. This is our exponential function. So we're going to estimate the slope of f of x equals 2 to the x plus 3 when x equals 2. We're going to go to 2 decimal places. We are not going to do, it's possible to take the derivative or difference quotient of a logarithm. We are not going to. So this is, in terms of functions we covered, where we're going to stop. We will do rational functions. We've done polynomial functions. Don't even have to worry about linear ones because they have the same rate of change everywhere. We just did a trig one. We're about to do an exponential one. The only other function we haven't covered is logarithmic functions, but we won't do that, so you don't have to worry about that. IROC equals the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. So again, this is going to be a weird one, just like the last one. So 2 to the 2 plus h plus 3 minus f of 2. When I put 2 into my function, 2 squared is 4 plus 3 is 7 all over h. 2 to the 2 plus h. 3 minus 7 is negative 4 all over h. You should, just to kind of flex your course knowledge, you should common factor as much as you can or simplify as much as you can for these questions. We did it with our trig example using a cofunction identity where you could have used a compound angle formula. I'm going to do the same thing, and we kind of did a question like this already in our logarithmic unit. So what you can technically common factor out of this is a 2 squared. And what does that leave you with? 2 to the h. So we're going to pause there for a second. Remember, if you were to work backwards, what we just did, you would distribute that 2 squared in. When you have like bases, what do you do to the exponent? You add 2 plus h. -4, that is just, if I take 2 squared out of 4, right? 2 squared is 4, that's just minus 1. All over h. What's 2 squared? 4. 2 to the h minus 1, all over h. At this point, that is as far as you can go, so we are going to do the exact same thing that we just did. Again, is it necessary to do those 2 extra steps? No, but it does prove that you have some knowledge of previous units. So I do want to see that for an exponential function for doing the difference quotient. So we still can't put 0 in, so we're going to cheat a little bit, and we're going to do just like last example, 0 decimal, 3 zeros, and a 1 into our function. Not plus 1, minus 1, sorry. That looks better, all over h. Put that all in to your function, so 4 times 2 to that, minus 1, all over that. 2 decimal places, you should get positive 2.77. Therefore, the IROC of f of 2 is approximately, now this is approximate because we didn't actually get h to cancel, we subbed in something really close to 0. So approximately 2.77. And again, if you think of the graph, it's always a good idea, self-check. This is exponential, 2 to the x plus 3. It's just moved up to 3. Does something like that, right? So f of 2, say, is there. It definitely should have a positive slope. Just a quick built-in self-check. Doesn't tell us the 2.77 is right, but it definitely would tell us we were wrong if we got a negative number there. Or if we got 0. So there's a lot to unpack. This is definitely something that you have to practice. Practice makes perfect for this, 100%. Your work, page 92, number 3. Now you're going to notice I have ignore what the textbook says, just do the difference quotient. Do as many as you need to become an expert. And then there's also some review questions for you to continue to work through. That's it for this lesson. Thanks for listening. Talk soon.